Hello.
Hi, Leah. People got out and there was some food there for the coffee break, so it's hard to bring
That's
them back.
fine. That's fine. I was just saying hi to people that are here.
I'll try to bring them back, but
No
I
problem.
can't.
Don't worry. Don't worry about it. Let them eat. It's fine.
Mañana no, viernes, ¿no? Bien, so ahí está. I think we can start, Leah.
No problem. Let people eat. It's fine. We are in no rush today.
Oh, they've been eating all day, so. So I'll leave the microphone with them here, so they can. I guess, right? We can interact. So.
So actually, I'm looking forward to this session because it gives us time to breathe and just reflect and just chat and get to know each other. So it's not going to be a lecture. It's not going to be, and neither the slides nor me writing on the board. So let me tell you what I was thinking of doing. So first, I just want to see how we are doing in general, what is interesting to us, what is difficult to us, and what is intriguing to us. And I want you to kind of get to know each other better. I mean, I'm assuming that you probably know each other well by now because you are always eating together and hanging together. But I'm thinking that ideally I would like you to maybe talk to somebody that you haven't talked before. So what I would like us to start with is let's divide into groups. So let's groups of maybe 3 to 5 people. And then within one group, I want us to chat about these things. I'm going to write them on the board so we will have like some talking points. Let's chat for like 10, 15 minutes or so. And then at the end, I would like somebody from the group to share with everybody else what you guys talked about. So how does that sound? Okay. Okay. So let's form those groups. Go around the room, take your seat, sit with somebody you've never met before. I know that there is like a group of people from Uruguay and a group of people from Brazil. So let's break those groups. Let's mix them up. It seems that this classroom is not ideal for group work, but And then let's talk about, so my general idea was to talk about following 3 things. So groups of like 3 to 5 people. So first thing is, what has been most interesting to you so far? And we don't have to limit this conversation to this conference only. So if you want, you can talk about what has been most interesting to you so far in terms of what you learned at this conference or this summer school, whatever. But it can also be what is interesting to you in general, right? So let's say interest. I will say also share memorable, most memorable. Or most inspiring things. So it can be about things that you just learn, but it doesn't have to be. You can share about any of these aspects so far in your like math education or math career. And then the second thing that I was hoping that it will inspire some actually more learning potentially is talking about what has been most confusing to you so far. Again, we can limit the conversation on what has been most confusing or most difficult that you have heard at this school, or it can be more general than that. So let's say, um, uh, let's how we want to call it. Let's call it just confusing. So share some confusing or some maybe challenging things. So you see, if one of you maybe was iffy about something that me or some other presenter said, and you share it with other people, they can give you the insight that maybe it is going to be more precious to you than, you know, if a speaker answer a question. And it will also create a dialogue, hopefully, and maybe you will learn something from that too. I find talking to people about math always helpful, and these people, they don't necessarily have to have math background. So sometimes just verbalizing what you're struggling with can be very helpful. And actually, you know what? Sometimes when I just say what is troubling me, I come up with an answer. So that's why I want us to talk about these things, right? And last and most importantly, I want us to talk about open questions, right? Because after all, this session is called questions. So let's talk about questions. Again, these questions, they can be related to talks, but not necessarily, right? You can mention maybe one question that you had and has nothing to do with any of the topics featured at this conference, right? So that's fine too. As long as we share the questions, that's fine. So again, this can be a little question, like maybe why is the Leavitt path algebra of this graph what it is? And it can be more general question, like open conjectures or some difficult topics. It's fine, as long as it's something that you are thinking about. So let's talk about these things among ourselves for maybe 10 to 15 minutes. And then I want one person from each group to tell to us all what you have been talking about. If you need to use the board, you know, go ahead. In the meantime, just so that I'm not bored, if anybody has a question for me, feel free to to ask me also. I'm kind of bored here, so I'm just checking if maybe somebody finished the discussion and we can talk about it. Or if you need more time, that's fine too. Just wanted to check how you're doing. So do you think you are ready or you need more time?
We are ready, but there are some groups that are still talking.
Okay,
So
let's then do 5 more minutes.
okay.
In the meantime, while these other groups are talking, still talking, if the four of you have any questions for me regarding the lectures that we had, or if you would like us to go over some problem, we can do that.
All right, we have a question.
Oh, sure.
Yeah, first of all, thank you for the lecture. It's really great. I didn't know anything about the topics and I found it really interesting.
No, I'm glad, very glad.
My question was regarding whether, well, I don't know anything about algebra to start, but my question was if I start with a ring, how could I know if there's some necessary condition for it to be isomorphic to path algebra, for example, if I solve it?
Uh-huh. Uh-huh. So the question is whether one thing is isomorphic to another thing in general is super, super difficult. So you see, that's why actually people want to come up with all these sorts of invariants so that can help them classify things. Because just to determine whether two things are isomorphic or not, that's like super difficult. So you see, that's why people came with like representations, and that helps us kind of figure out if at least things are represented the same way or not. Or they come up with these invariants. One of them is k0, and then kind of this boils down to this, right? So your question in general is way in this category, right? Super general, super difficult, and super interesting. So there is no like definite answer. This is the method how you can determine whether a ring is isomorphic to Leavitt path algebra. But I can tell you something that may help. So Leavitt path algebra has this thing called universal property, which means that if you can somehow find a way to map vertices, edges, and ghost edges into some ring R or algebra R, and you make that, like, let's call it actually let's call that V you map to AV, E you map to BV, and E star you BE, and E star you map to CE star, let's say, where AV, BE, and CE star are in your ring, the one that you are maybe having some doubts that it may be isomorphic to Leavitt path algebra. So if you can make such a map, and if these three groups of elements satisfy the same axioms that your Leavitt path algebra has, so those 5 axioms, right? V, E1, E2, CK1, and CK2, then you know that there is a map from your Leavitt path algebra to your R. And if you, so this is called a universal property. So somehow everything is determined only on these basis elements. In a way, that shouldn't be surprising, right? Because these are generating everything, right? And one more thing that may be useful to you, there is also something called like uniqueness theorem that is saying if this map here from V to A to V is 1-to-1, in other words, if this AV is not equal to 0, if the images of your vertices is not equal to 0, and either this map agrees with the grading that we are going to talk about later, or some other property for graph has, then, so I will just say plus one more condition. then you know that this map is one-to-one. So in a way, you know that there is a copy of your Leavitt path algebra in R. So in general, when people are trying to prove that Leavitt path algebra is isomorphic to something else, then this helps, and this helps, and somehow you have to show that every map in here has the original there, and then you pretty much have the isomorphism. So you see, when I was talking how Leavitt path algebras are equal to these matrices, I will erase this part here. You can kind of convince yourself that that's true based on something like this. So for example, this graph here, right? One edge looking like this, we now know that it is isomorphic to M2 of K, right? And the way how I was convincing you that that's true is pretty much I mapped only these things, right? We didn't go to, I mean, here there is not much else to start with. So this isomorphism here, I was writing like, if this is U and V, I was writing U, V, E, and E star, right? So you kind of see how you can handle with like basis elements. But in general, if your graph is bigger and fancier, pretty much this is kind of how you want to do it.
Yeah. Okay. Thank you.
Do you have some other questions?
The other question that we had is, where is the dynamics in all of this? Because until this moment, we saw a lot of algebraic properties, if you want, but we don't know how can you go from algebra to dynamical systems. What properties of the dynamical systems you can see in algebra, for example.
Okay, so maybe I'm not the best person to talk about it because I never crossed that bridge. I mean, I wasn't crossing it a lot myself. So the relations with dynamics, the best relations that I can tell you about so far, based on what you know so far, is in another way how you can define K0 of Leavitt path algebra. So somebody was asking about incidence matrix. Was it? No, it wasn't this morning. I think it was yesterday. So the incidence matrix again is so you index. Think that rows and columns are indexed by vertices. So let's say that we have n vertices. So this is v1, v2 up to vn, v1, v2 up to vn, and then if from vi to vj there are ni vertices, then you put ni. Let's call it nij. Nij vertices, then you put nij on the ij spot. So this K0 is co-kernel of map that is determined by I minus A transpose. So there is the most dynamics I can think of is in this map here. So I will direct to two people to talk more about dynamics. One is our conference organizer, Gonçalves. I'm not sure if he's in the room, but he's a good person to talk to about that. And the other is Rusbeh Hazrat. So
Daniel, you mean Daniel?
Daniel, yeah, Daniel Gonçalves, yeah. And the other person is Rusbeh Hazrat, who is going to give talks next week, right? So he can. He has a paper titled "Dynamics of Leavitt path algebra," so he can tell you more about that. Other groups, how are we doing? Are we still kind of chatting or?
Hi, Leah.
Hi.
No, I think you're not seeing me.
Yeah, but I hear you.
We're off camera. Now we are here.
Hey.
Hi. So we talked about how we were enjoying very much your course,
Oh,
and
right.
that this was a very interesting part of it. We were we also were finding it a bit confusing sometimes to look where was the objects or the dynamic beneath all the things we
Uh-huh.
were learning about and talking about. Also, for example, in your course, we were talking about the um, like the characterization of the Leavitt path algebra by the direct sum of the matrices and those stuff. Something like that. We talked,
So was that confusing? That characterization was confusing or interesting or both?
both.
Okay.
Both and like we decided that today was a day to like spend time thinking and discussing about it and trying to figure it out and understand it better.
If you
So
want, we can do a few examples together now. We still have time, so we can
okay,
do a few examples. Yeah.
yes. Well,
So,
we try.
what kind of questions were members of your group having in like category 3? I'm thinking.
There was a question about the axiom CK1, the one that says E is star is source of E. But we figure it out.
Great. That's the best part.
We
Uh,
started with it, and we were thinking like, why was it necessary? And then we nothing. We talked about that if you don't have that axiom, then E star is just E star, and you like I don't know. We we think that the axiom captures the essence of the ghost path as like rewinding. No, that's not the word. I don't know.
no, I understand completely.
Like going backwards, but not by another edge, but by the same edge. So that's what
Awesome.
we talked around that question.
Awesome. Well, I'm actually now even more sorry that I'm not there so that we can chat even more together because your group seemed to be having an awesome time together.
Yes, we were fighting the language barrier, but it was good.
Awesome. Thank you so much for sharing this.
Thanks.
Hi, Leah.
Hi.
Sorry, I have no idea if you can see me.
I see kind of half of you.
Hi, sorry. It's a quick question concerning something you were saying this morning. At a certain point, while we were trying to compute the Grothendieck group, you said that it's generated by all the vertices V, and we should think to them as the module generated by V over the Leavitt path algebra.
You mean the relation between this and that?
Yes.
Uh-huh. So,
Okay.
so technically, I want generators to be any elements indexed by vertices. That's it, right? And
Yeah.
and I instead when you're reading papers that introduce this to you, they usually say AV, but I want to use this instead of that, just so that we are thinking, that's kind of isomorphism class that corresponds to has something to do with that vertex, right?
Uh-huh.
So that day, I think it was Monday, when we talked about what Grothendieck group in general is. I told you that it can be defined using finitely generated projectives, and it also can be defined via idempotent matrices.
Yes.
So if you're considering this as like one times one matrix, this is an idempotent, right? So you actually don't even have to add anything else, right? This is an idempotent, so it is one by one idempotent matrix, right? So if you are introducing K0 via idempotent matrices, you don't even have to write anything else. That's it, right? And if you are introducing K0 via finitely generated projectives, then if I have idempotent, I don't want to say E because now we are using E for, for edges. Let's call it P. So in general, if you have a ring R, and if P is element of R such that P square is P, right? If it's idempotent, then this module here is finitely generated projective. Why? Because this is finitely generated free, and this is direct sum of it, right? So that's why this is finitely generated projective. So this is finitely generated projective, right? By putting brackets around it, I'm thinking isomorphism class of that finitely generated projective. And then just you can just argue, well, I'm sick and tired of writing this all the time, so I just write V. So that's why we write only V, right?
Oh, okay, but I can convince myself why all the simple projective are of that form, but I cannot see why all finitely generated and projective are of that form.
So that's that argument that requires more work. That's not something that I can tell you about in even in next 20 minutes, I think. So we would need more background for that, right? So maybe one way to maybe kind of, informally you can convince yourself is that so every finitely generated projective is somehow direct summand of finitely generated free generated with n things, right? So every finitely generated projective is direct summand of something like this, right? So after all, here I have that vertices are main stars of the show. So maybe, vertices listed n times or something if this is n, but, still vertices are my like generators and everything I can express in terms of vertices. So somehow, this would be a difficult argument. Somehow the direct summand also needs only the vertices, right? But at least, what you should trust at this point is that this requires only vertices.
Okay, is it something related to the fact that these are algebras of graphs?
That's right? Because think about what are generators of this thing here. They are vertices, edges, and ghost edges, right? And since these are I want you to think of these as kind of ways how to connect two projections, right? So this is one projection, this is another projection, and in world of Grothendieck groups and idempotents and all of that, two idempotents are kind of relatable, and they give you the same class in isomorphisms in monoid of this monoid before you go to K0. So this relation here is defined if there is xy such that xy is p and yx is q, right? So if you go here not using finitely generated projectives but using idempotents, then this would be a relation that tells you when two things are going to be considered equal in here. So you see, that's why these two things, and this one is actually a vertex. We know which vertex. This is the range of E, right? And this one kind of has to do with source of E. I don't want to say equal to source of E, but it has to do with source of E. So certainly that source of E has direct summands equal to these things here, right? And this is already a vertex. So because of relations like these, vertices are all that you need, pretty much. Actually, I can give you even better argument for this part here, right? So if our, first of all, everything is generated by vertices here, right? That's how we define that graph monoid ME, which ultimately is isomorphic with this, right?
Okay. And
here we have that V is equal to that EE star, right? And then some can go outside. And then we can switch these around. We talked about this today. And after all, this is now a vertex, right? Because this is a range of E, right? So somehow, vertex, that's why they end up being enough.
Okay.
Because these two are equivalent in this sense. So actually, if this is not equal to a vertex, it ends up being equivalent to a vertex, right? So yeah, that's maybe then good argument. So somehow you see these like edges, these partial isometries are relatable to vertices as well.
Okay, in this case, this made my second question unrelated to the first one, as it was supposed to be. But are Leavitt path algebras semi-simple in some sense? I see they are not matrices over domains, but they are matrices over graded domains.
Right. So this one here is not. So if your graph has no cycles, then Leavitt path algebra, and let's agree to talk only when you have finitely many vertices, so that there is just one around, right? So then your Leavitt path algebra ends up being just sum of matrix algebras over fields, so that's definitely semi-simple. But somehow when you have these cycles with exits, that ruins it for you. That won't be semi-simple anymore.
Yeah, now you remember it's isomorphic to the direct sum, so cannot be finite dimensional. Okay.
I can also tell you, since we are talking about ring theoretic properties, I can tell you about one very, very popular trend in world of Leavitt path algebra. So one big line of research is to fill the blanks in here. Leavitt path algebra is such and such, if and only if graph is such and such. So at first I thought that, when I first started learning about this, it was interesting and it was fun, but it wasn't really that much more for me, right? So we can play with graphs and algebras and fill these blanks, and people filled it already in a lot of ways. So for example, semi-simple that you mentioned, that's why I thought of it. It's known exactly when is Leavitt path algebra semi-simple. It is semi-simple if and only if graph is, I don't know, acyclic and such and so on. So if you put here regular, if you put here Noetherian, if you put here bare, if you put here whatever, all sorts of ring properties, people figured out the graph properties when that holds. So when I was first learning about this, it was kind of nice and fun, but I didn't really grasp some larger significance of that. These days, whenever I need to produce a bare star ring that is not, I don't know, bare, or the other way around, bare ring that is not bare star, or regular ring that is not Noetherian, or Noetherian ring, I mean, all sorts of examples like this. I don't even think in terms of ring theory anymore. I just go to Leavitt path algebra. Okay, so we want a regular and let's say a not Noetherian. So I find a graph that has a property that corresponds to regular and doesn't have property that corresponds to Noetherian, and there it is. So actually, if you get familiar with this, word filling here, you will have actually much easier time in ring theory in general or algebra theory in general producing rings or algebras that have certain property and fail to have certain other property.
Okay, in this direction, what can I say about the Leavitt path algebra if E is a groupoid?
If it's a groupoid,
yeah, does it inherit a Hopf-algebroid structure or possibly a Hopf-coalgebroid structure since it's
so Leavitt path algebra is just like a special case, right, of groupoid algebra. I think that somebody is telling you about that in other lecture, right? Or I'm mistaken?
No. We have also a lecture on groupoid algebras.
Okay, so there is kind of extended version of this, which is saying this groupoid has such and such property if and only if whatever algebra, Steinberg or something has some other property, right? But as I was mentioning at one point before, for me, this is already, open enough. Me personally, I never went further in those further generalizations. So I will not be the best person again to talk about these like fancier stuff. just this level here.
Okay, thanks.
Hi, Liam. I'm with a question. If when you construct the Leavitt path algebra, you construct first that ghost edges in order to make them partial isometries in the algebra. Then every edge is a partial isometry, every vertex is an idempotent. Then is there an inverse semigroup? Probably you have to put a zero in that inverse semigroup, that in such sense that Leavitt path algebra is a semigroup algebra of certain kind.
So if you consider only elements of this form, right? There are some type of generators, right? Leavitt path algebra is definitely span of these elements here, right? So this is your entire Leavitt path algebra. But if you don't want to go to algebra, if you want to consider just the set of these elements with multiplication, which is kind of concatenation, right? Then these form an inverse semigroup, I believe, right? Because think about what think how you would fill the blank here. You can fill the blank here, and then it has the structure of inverse semigroup. So there are, I think, not that many, but there are a few papers that study only these, like, generators without the plus and without the algebra structure, right? And certainly without any k around. Here, when we are looking just at these and multiplication, we don't have k around.
Okay, is there this same group has a name in the literature or have
it's
some
called, I believe, graph inverse semigroup.
Okay, thank you very much.
Sure. Do we have some insights from all of you, like as a group, in terms of questions? Your group.
This is more or less two groups which are seated more or less in the.
Okay. Okay.
We already spoke.
Hi. We wanted to say that we love the pictures featured in your notes. So thank you for that.
Oh, we are still going to get to apples. Apples are really important. Apples are super crucial for understanding these gradings. We'll get there tomorrow.
All right. ¿Verdad? Creo que se está terminando. I think it's we're yeah. So
La única que entiendo la pregunta no habla inglés.
I see that somebody has a question from our online participants. So Igor, if you have a question, feel free to. Oh yeah, absolutely, you can ask a question. Absolutely. Feel free to unmute yourself and talk, or feel free to type it in the chat line. Whatever it's better for you. Okay, actually, so my plan was to talk about representations of Leavitt plus algebra on the last day. But I can tell you, we are going a little bit behind. I don't want to rush things, because if I rush things, then we will, lose a bunch of stuff that otherwise we will understand. But on the other hand, the story started as graded classification conjecture, so I would first finish that, and then we will see how much time we will have for representations. So regarding representations of Leavitt plus algebra, the irreducible ones are known. So irreducible representations of Leavitt plus algebras are known up to equality of their kernels. So if you're thinking all irreducible representations and two are not really equivalent in that stricter sense, when two representations are said to be equivalent, but two of them have the same kernel, then it is known that there is exactly 4 representatives, nice representatives from these 4 classes. And I was to give you an overview how these 4 are defined. So if we don't get to that, that's in my notes, so you will be able to take a look. And then what I wanted to tell you about is the graded version of this. So irreducible graded representations. And that is as fresh line of research as possible, because it was pretty much done months ago. So this is really fresh from the press. So it turns out that there are also 4 classes, not the same 4, but there are 4 defined representatives. And if you look at the pictures at the very end of my notes, that's the sink, infinite emitter, infinite path, and fancy bicycle called exclusive cycle. So these are the 4. So if you think of irreducible representations as, in a way, building blocks, then the answer is that most about them is known. Again, this is weaker sense of equivalence. They just have the same kernel. They are not, equivalent in that stronger sense that usually people use. But I'm not sure if I will have time to tell you about details, so we will probably just leave it at the notes. So I see that we are out of time, more or less, but I can still go over the examples that our first group was talking about, like doing more examples of these matrices. If you want, it's up to you. So, I mean, I can do an example, and those of you that, want to take a break, it's no, like, not necessary to sit here. It's up to you. If anybody else has any other questions, I can still answer them.
Okay, so yeah, we'd like to see the examples.
So more no exit graphs, and how to tell, which matrices they are isomorphic to. That's what you are thinking. So let me try to come up with a fancy no exit graph, and then we'll do it together. And then I will still leave the one from the notes. Let me just give you the page number and everything. So let me just open my... Okay, so now I'm doing something like example or exercise 9 on page 10. So I'm going to take something that looks like that last one, which looks the fanciest, and I'm not going to take this one. When I'm working with my students, I'm calling these problems like twin brothers. So I'm not going to do exercise 9, but I'm going to do twin brother of it. So that means that it's similar enough that you will be fine with with the one from my notes. So let me make it even fancier. Let there be 2 sinks. Let there be 1 cycle, and let's do length 3. We didn't have that before. So let's say that we have something like, let's say that I have entrance here, and let's say that I have entrance here also, right? And let's say that and from here I can go there, and from you know what? Let me make this a source. How about this? Okay, so what am I looking at? I'm looking for sinks and cycles, right? Sinks and cycles. So there is 1 sink here. There is 1 cycle here. And I have to pick 1 vertex of this cycle. Let's pick, I don't know. Let's pick this one here. So that means that there will be 2 summons. M blank of K. So that corresponds to this sink. Right? So the fact that there are 2 here is because I have 1 sink, 1 cycle. I pick an edge in this, I pick a vertex in this cycle, right? And then this sink here gives me that. And this cycle here is going to give me another term. And here it's going to be Laurent polynomials. So if I'm not interested in graded world, right, I just need to count how many paths. So here it's number of paths ending in the orange vertex. And here I want to count the number of paths ending in this blue one. But without counting the whole cycle. Right? And just keep in mind, this game that we are playing here works only for no exit graphs. So if my graph is maybe that this arrow is reversed, that would be an exit. That everything that I'm telling you falls into water. It doesn't hold, right? So for this to work, your graph has to be no exit, right? If this is reversed, that's an exit, then everything that I'm telling you doesn't hold, right? So graphs have to be no exit for this to work. Okay, so let's count how many paths end here, right? So I always have 0 path, and then I have this one, and then I have this one. So that's 1, 2, 3, and then I have this one, 4. So 4 total ending there, right? So this will be 4. And here I have, this has to go in, not out, right? Now it's no exit. And here I'm counting how many end there, right? So this is 0 path, this one here, this one here, this one here, right? And then this one. So that's one more. And then this one. And then this one. So if I counted well, and if I didn't, you will correct me. So far I have 1, 2, 3, 4. I don't want to count this whole thing because the rule is without the whole thing, right? So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So that would be that. So try to do something similar in this exercise 9, and then we can talk tomorrow more, if you have questions about this. I have solutions, but as I advise my students, I also will advise you, try to first do it without peeking in the solutions, because you will learn more, and then if you're iffy about, you can take a look at the solutions. Do we have other things that we want to do, other problems?
Any more questions, guys? Group in the back, any more questions? You do? Great. Oh.
Hey, Professor Leah.
Hey.
We have a question, but we don't know if you talk about that. We was wondering, first, thank you for your beautiful talk.
Oh, you're welcome.
We was wondering if, like in quivers, we have for representations vector spaces in the vertices, yeah, and the rows are morphisms, and we are interested in irreducible morphisms. So in the Leavitt paths works the same. We can see the representation, thinking representation of Leavitt paths in the same way like in quiver representation.
Yeah, because quiver is directed graph, right? So if it's really tomato if you call it quiver or directed graph. So if you're more familiar with that language, everything that I'm saying is pretty much a oriented graph, so it still holds.
And I don't know if this question have some sense, but for example, I can think in the Auslander rate and quiver in the same way too.
Well, I'm not sure about that really. I'm actually not sure that I know which quiver is Auslander, right?
Okay. Okay, thank you. That's it.
Sure.
You guys have any questions? Oh, that was great. I think that worked very well. All right. Thank you, Leah.
You're welcome.
Thank you very much.
Well, see you tomorrow morning then.
Yes. Good evening or good night there. See you tomorrow. Thank you. Bye.
Bye.